Okay, so hi there folks, so we're now in our next video in number theory, and here we're going to talk about our continuation video in our topic in the Chinese remainder theorem, and here we're going to solve Sun-Tzu's puzzle now by iteration. Okay, so um, looking back to the Sun-Tzu's problem, I'm going to state it here. We will be finding a number that leaves a remainder of 1 when we divide it by 3. It leaves a remainder of 2 when we divide it by 5, and it leaves a remainder of 3 when we divide it by 7. So let's provide a solution for that. So it's just obvious that we'll be using the congruence language to solve this kind of problem. So we will be finding x. So in short, we will let x as an integer to be part of the integers, such that this x, okay, in the first statement, it leaves a remainder of 1 when divided by 3. So in the congruence language, when it leaves a remainder of 1, it's just enough to say that it gives a 1 mod 3. Okay, it leaves a 1 on the right hand side mod 3. So when we divide it by 3, it will leave us a remainder of 1. In the second statement, it leaves a remainder of 2 when divided by 5. So x is congruent to uh, this remainder, which is 2, congruent to 2. Okay, it is congruent to 2. Just a moment. Mod 5. Okay, and also it leaves a remainder of 3, so x is congruent to 3. Okay, 3 mod 7. Okay, so that's our translation of this statement here of Sanchez puzzle into the congruence statement. So how do we solve this by iteration? So we first look at the first statement, x is congruent to 1 mod 3. So by theorem 3.1, so we take x is congruent to 1 mod 3. Okay, since that is true, so by theorem 3.1, 3.1, we say, or we remember theorem 3.1 is something that that congruences are somehow like equalities. We just need to have the tweaking using the division algorithm to find such. So by theorem 3.1, you can just rewatch the theorem if you want. So x is equal to, now using the equal sign, 1 plus 3 3 times t sub 1 for some t sub 1 as an arbitrary integer. So let's move it here. Okay, for some 1, this is t sub 1. Okay, for some integer, for some t sub 1 in the integers. Okay, now since x is equal to 1 plus 3t, if you want you can recall that this x when divided by 3 is equal, it has a remainder of 1. So meaning by the division algorithm we can say that x is equal to 3 times t sub 1. Okay, we divide this x by 3, of course with another factor, plus the remainder 1. So just by commutativity, this becomes x equals 1 plus 3 t sub 1. Okay, for some t sub 1 in the integers. So we substitute the value for x, since we know x is equal to 1 plus 3 t sub 1. We will substitute this to the second congruence. So substitute the value of x. Substitute x in the second congruence. In this is x rather. In the second congruence. Okay, so if we're going to substitute the x in the second congruence, we have the second congruence as x is congruent to 2 mod 5. So that is x is congruent to 2 mod 5. Okay, so if we'll do that, we have um, since x is we have x is congruent to 2 mod 5, so let's write that first. So x is congruent to 2 mod 5. Substitute the value of x there. So we know our x as this one. Okay, so we know our x is this one, so therefore what we have is 1, 1 plus 3 t sub 1 is congruent to 1 mod 5, 1 here. Okay, so what we want to do first is to clear out and get the value of t sub 1 as a congruence. So therefore, um, subtract both sides by 1, or rather this is 2, sorry. This is 2 so also. Okay, so subtract 1 to both sides to get rid of this 1. So minus 1 here also. So this leaves us with 3 t sub 1 congruent to 1 this time, mod 5. Now, we want to isolate or make the value of t sub 1 to be isolated. So there will only be t sub 1 on the left hand side. But here we have 3 t sub 1. So we need to get rid of this 3. So how? Cancellation is not easily done in the congruences, but we can make some ways to do that. For instance, we know that this is mod 5. So meaning all the values beyond 5 with 1 plus 1 is going to be 1. So for instance, 6 is equal to 1 mod 5. Okay, 11 is equal to 1 mod 5. Okay, 16 is equal to 1 mod 5. So we need to find those numbers in such a way that it will make it 1 here. So what will we do? Imagine multiplying this by 2. So if we multiply this by 2, we also multiply this by 2 on the other side. So if we're going to do that there, this becomes 6 t sub 1. So 6 mod 5 is 1 t sub 1. So that leaves us with only 1. Okay. And 1 times 2 is just 2. So therefore, we have this answer. This is by the power of theorem 2. So when we have A is congruent to B mod 5, so we have a C there in which we're going to multiply them. So AC is also congruent to AC, or BC rather, mod 5. Again, so that's by theorem 3.2 or theorem 3.4. That's a redundancy, right? So that is using again. So again by theorem 3. By theorem 3.1 by theorem sorry, theorem 3.1, we will convert this into an equation. So I think you know what will happen here. We have t sub 1 is equal to, okay, it's equal to 2 plus 5 t sub 2. Well, with another t sub 2 in the t sub 2 in the integers. Okay, an arbitrary t sub 2, by the way. Now we will try to merge these two values of x or now we're going to get the value of x now, okay? And we're going to substitute the value of t sub 1 there, okay? To get the value of x and substitute this value of x now to the third congruence. So what we'll do is we know that x, load it down, x is equal to 1 plus 3t sub 1, okay? And we say the value of t sub 1 as this one. So we will substitute the value of t sub 1 there. So we have 1 plus 3 times 2 plus 5 t sub 2. So by distributivity, what we have is 1 plus 6 plus 15 t sub 2. So fix this. What we have is 7. 7 plus 15 t sub 2. Okay, so that's the value of our x. Okay, 7 equals, or rather, x equals 7 plus 15 t sub 2 for some t sub 2 in the arbitrary integers. Okay, so we will substitute this value. Now substitute this value. This uh, to the third equation, or third congruence rather. Don't use the word equation here. Okay, so the third congruence. So therefore, for the third congruence, we know that it is what was that again? X is congruent to 3 mod 7. So let's write it there. X is congruent to 3 mod 7. It leaves a remainder of 3 when divided by 7, right? So we know X as 7 plus 15 t sub 2 is congruent to 3 mod 7. So we find ways to get rid of this 7 here. So we deduct 7 from both sides. So this will leave us 15 t sub 2 in the left hand side. But how about here? What is 3 minus 7? So 3 minus 7 is going to give us minus 4. Okay, so it's going to give us minus 4. Um, but then, so 3 minus 7. Okay, but if we're going to minus 7 here in the 3, it's again, it's modulo 7, right? So it's modulo 7. So if we're going to do that, it's like we're going back to 3 again because it's one cycle. Okay, it's one cycle, so it's a 7, right? So this is going to still gonna be 3 mod 7. Okay, since it's one cycle of the modulo, it just so happened that it's like that. Okay. Um, then again, what do we have? It's going to be, we're going to find ways in such a way that 15, this 15 here as a um coefficient, as a coefficient will be will be we will get rid of it. We will get rid of it. Let's erase this one. We'll get rid of it. And we're going to multiply that by some number in such a way that if it's going to be modulo 7, it's going to leave us with the remainder of 1. So what number is that? Actually, 15. If we're going to apply modulo 1 there, because we have 7, 15 divided by 7 is 2 remainder 1. So that's the remainder actually. We don't need to multiply that with anything. So t sub 2 is congruent to 3 mod 7. Okay? Now with this, so we say by theorem 3.1 again, we say that t sub 2 is equal to Okay, t sub 2 is equal to 3 plus 7 times this something, and we will call this t right now. That is for some t in the arbitrary integers. Okay. Now, therefore, we will be, since we have applied all the congruences from first congruence up until the third congruence, I think it's due time for us to make this official. We will get back to the value of x again. So we have x. So therefore, oops, sorry. Therefore, so x, oops, sorry, x is equal to, remember the value of x as 7 plus 15 t sub 2. So substitute the value of t sub 2 as this one. This is equal to 7 plus 15 times 3 plus 7 t 7t, okay, equals, just distribute the 15 plus 15 times 4, 15 times 3 rather, it's going to give us 45. 15 times 7, what's that number? I don't know. 15 times 7, what's that? 7. We have 35, so that's 105. Okay, plus 105, 105t. Okay, so therefore we say um, that x is equal to 45. 45 plus 7 is going to give us 52 plus 105t. So therefore this is our answer for our x. So what does this mean? Thus, any integer in the form x equals 552 plus 105t, okay, any integer, any x in the integers is a solution of the linear system, of this linear system. Of this, need to make some lines here, of this linear system of congruences. Okay, and actually this is called the general solution of the system. The general solution of the system. Let's put it here. Okay, just take note that you can see that the mod, okay, the mod or the coefficient of 105, okay, because actually our solution is x equals 52, x equals 52 plus 105 t. We can make this as a system of as congruence. So our answer again is x equals 52 plus 105 t. We can do this by theorem 3.5, 3.1, sorry, theorem 3.1. This becomes x is congruent to 52 mod 105. So this is the general solution of of our of our linear system. Notice that 105 here, 105. Note that 105 is equal to, okay, 3 times 5 times 7, which are actually the mods of the three individual congruences of this linear system. So in this example, we have a unique solution 52 to the puzzle and the modulo 105. The modulo is 105, where the moduli are or is a pairwise relative prime. Okay, it's a pairwise relative prime. of the previous modulo of the congruences of the system. So this will give us as a springboard for the Chinese remainder theorem. This is in honor of the early contributions of the Chinese mathematicians to the set of congruences, or to the theory of congruences, our theory that we're talking right now. It shows that every linear system is the same in the same single variable with pairwise relative prime moduli has a unique solution. So Sun-Tzu's puzzle is one of the earliest actually instance of the Chinese remainder theorem. So a general method for solving such linear system can be found in the Mathematical Treatise in the Nine Sections as a book written by Xin-Chiu Xiao in 1247. So um, we will be we will be following this video will be followed by the Chinese remainder theorem proper, so that you can see the power of that theorem. That theorem is one of the one of the basic theorems that one must know in order to go further, okay, in this subject, in this field of number theory. So thank you for watching this video. This is again by iteration, but we will be using some powerhouse theorems after this video. So thank you very much for watching. I hope that you would like and also subscribe. Okay, thank you.